Hey there. Okay, let's see how this works out for me. Alright, so this right here is going to be the work for each of these problems, and I just went ahead and did all the problems as a single video and as a single PDF because they are very, very interrelated. So all of these problems are Henderson-Hasselbalch problems. They all use the Henderson-Hasselbalch formula. And really, they only differ in how you treat this resulting overall A minus over HA number that you're going to get. So in each of these, you have to do slightly different things with the number because they each ask for slightly different outputs. All of them are related to this, but you know, you have to do a little work on. All right, so this is the first one. This was 19, which was this question, of course. You can read that question. There's also the PDF that says 19, 20, and 29 if you don't want this moving video. That makes it harder to write sometimes. Okay, so this right here, in each of these, I'm going to write this down. This is the Henderson-Hasselbalch formula. pH equals pKa plus the log of A minus over HA. So right here you have the pKa. This is the book value for that acid dissociation constant. This right here is your pH. This is the actual pH of your conditions. So for example, right here you have a pH of 4.541. And then finally we have the log. This is the log base 10 because these are both log base 10 numbers. So plus the log. So you have book value plus log of. And then this A minus, this is the stuff that's lost its H place. So this is the ionized form of whatever acid you're talking about. Or another way of thinking that is this is the conjugate base. And this right here then would be whatever amount of HA, which is your acid, that didn't come apart. Okay? And if this sounds familiar, it's because it is. There's covered a little bit in the beginning of Organic 1. We reviewed it. But this is actually stuff that you learned back in Gen Chem 2. Okay? And you learned a little bit of it in Gen Chem 1, in fact. But you really concentrated on it. Probably in most schools you would have concentrated 3 chapters. Sometimes it's 4 chapters. And sometimes it's only 3 chapters. But you actually spend a lot of time on this sort of stuff. All right, so we have our pH. I put that value in there. We have our pKa. We're looking for actually this right here. This is going to give us numbers that we can work with to get our answer. And so I've plugged this in. I'm just solving the formula down here. I want this stuff in here, so I subtract that off first. That gives me that number. To undo a log base 10, you just take 10 to the power of whatever's there, and 10 to the power of the log, which cancels. And so I've taken 10 to the power of this number here. That's that. And then my log's gone, so I just have this resulting values that are in these parentheses. I went ahead and did that in my calculator. That's 1.45. If you're trying to take the MCAT, by the way, I'm just mentioning this, you need to learn to do logs in your head, actually. Which you can ask me about if you want me to explain that further. Anyways, so we get 1.45 here. That 1.45, that is the multiple of A minus versus HA. So we can say, well, we want the number for both of those numbers there. But we can go ahead and assume a number. So what I'm going to do is I'm going to say if HA was 1, so my denominator was 1, that would make my A minus 1.45. And that's just how fractions work. If you are having troubles with that, please let me know. I can explain it in further detail. But I'm going to assume that basic fractions is something you mostly remember. Which, trust me, there's a few times in my life where stuff that I mostly remember is not so well remembered. So don't feel bad if you don't. All right, so what we're looking for, though, is we're not looking for a concentration versus another concentration. We're looking for a percent not ionized. So what percent of the acid is not ionized? And the percent of the acid that's not ionized, that's going to be that HA actually. I know I accidentally put A minus here. I just forgot to correct that. We're actually looking for the HA. And that's going to be, well, percents are whatever you have over the total, right? And so it's going to be the HA over the total amount. All right, so I said my HA was 1, and then the total amount's just these two added together. So it'd be 1 plus 1.45. And then it's percentage, so we have to multiply by 100%. We do that, we get 40.8%. And we actually have to round to get the 0.8, but that rounds up to 0.8. It's no problem. And so we find out that the answer in this case is 40.8%. Keep in mind that whenever you do these works, I'm always going to show these for numbers that you don't have. Okay, it's the same problem, but these numbers change depending on the person asking the question. They're randomized numbers. So you have to do this work with your own numbers. Okay, I'll never actually show you. I try not to show you problems with me using your numbers, because quite simply you don't learn anything from that. You just put in what I put and then you go on and don't learn anything. So this works much better because you actually learn how to do the problem by actually running through and doing it at least once. Okay, so again, this is just another Henderson-Hasselbalch problem. There's the problem again. You'll see again, how do I know this is a Henderson-Hasselbalch problems? I want something to do with concentrations of my acid, or ionized portion of my acid, or not ionized portion of my acid, or something to do with that. And I've been given a pKa and a pH in some sort of buffer system. What does buffer system mean? Well, it's a weak acid, like so, that has a weak base, like so, that is in equilibrium, like so. So this is another buffer system. A big hint on this is your blood here is the buffer system. This right here is actually just talking about another buffer system. And the last problem actually refers, HEPES is a very popular buffer that you use in biochemistry, actually, in biological projects. Okay, so I look at my pKa right there, I plug that in to my Henderson-Hasselbalch. I look at my pH right there, I plug that in. Again, I just set this up. I'm looking for this A minus over HA again. So I go ahead and solve it, subtract that over, take 10 to the power of that, and that gives me 3.1, which is my A minus versus my HA. Now, if you notice, what this asked for actually is the lactate, which is this. Notice this has lost an H+, so that's your A minus. That's what those things mean. HA and A minus literally means a weak acid, HA. It loses its H+, that would leave you with an A, notice the A, and a minus because you've lost a positive charge. And so this right here is your HA. This right here is your A minus. And so lactate, A minus, lactic acid, HA, and there you go. So you're actually just literally looking for that ratio in your Henderson-Hasselbalch. It's actually the easiest problem of the three. Okay, now we get to the longest problem of the three. If you notice when you're doing these achieved problems, they actually build up on one after another. So the early problems will directly be using something that is part of a concept like Henderson-Hasselbalch buffer systems. And then when you get up into the 30s usually, those problems are the ones that will start combining concepts. And so in this case, we're doing a Henderson-Hasselbalch problem, but we also are going to have to do a significant amount of work to the number that we get. So it's combining concepts and problems to make a longer, more difficult problem. And this is 29, by the way. So again, Henderson-Hasselbalch, I have my numbers here for a Henderson-Hasselbalch buffer system. This is a buffer, by the way. And I go ahead and solve that. So I get 2.188 as my A minus over HA. I'm going to go ahead and set things up to get it all ready to solve. So I look at my HEPIs. I want something to do with KOH. I'm probably going to have to get into some sort of moles, because that's how reactants, substrates, react with each other. They go through moles. You can't really do anything directly through grams. And so an easy way to sort of set yourself up is you probably need to get into moles or molarities with things, okay? That will get you some more set up. And so specifically with this, I knew I'm going to have to use up some amount of that. And so I'm going to need my moles here. And so I took my molar mass here, I put moles on top. So 1 mole is 238.306 grams. And I'm just using that relationship right there. I'm literally just using the definition of it. And I want to get rid of grams and I want to be in moles. And so I multiply that number times grams. That will cancel the grams. And I go ahead and do that. So 4.5 divided by 238. That gives me 0.01888. And that's my moles and my HEPIs that I started this thing off with. Okay, so the third part then I need to do is, if we're in a single solution here, then my volumes for these two things has to be the same, because it's the same beaker, it's the same solution, right? My volume can't be different for two things that are in the same solution, because the solution volume is the solution, the entire thing. All right, so what that means is that these concentrations here that are typically in molarity, well, I could just as easily have these in moles because they're the same volume. The volume cancels. And so that number there, that 2.188, that's also the ratio of my moles. So I have 2.188 moles of A minus would equal 1 mole of HA, which I went ahead and solved here. I just multiplied that over, and that gives me my ratio between those two. Well, I also have another concept that I can suss out of this that I can use. And so that is that my HEPIs here, my total moles of HEPIs, which I figured out right here, well, that's 2 parts in solution. That's the HA, that's my acid, when it stays together. When it disassociates, that's also the A minus then, okay? And so the stuff that stuck together and didn't come apart is the HA. The stuff that came apart is the A minus. And those are my only sources, is this initial source of HEPIs. That's it. And so my total is this number right here. And I just need to subtract one of these off, and then I can plug one of these formulas into the other. And so I went ahead and subtracted off the moles of A minus. I did that so that I can substitute this into here easier. And so I went ahead and then substituted. I took that 1.88. I substituted moles of HA, which I said moles of HA is this right here. I put that in there. And then that equals moles of A minus, like I said it up here. I then did the math, so I multiplied these two numbers together. This number then goes in front of moles of A minus, and that's that. I then add over this number, and so that's 1 here, that's 2 here, that's 3 then down here, and I still have that same number on the left. To get moles of A minus on its own, I go ahead and divide over 3.88. So 0.04 divided by 3.188 is this number here. That is my moles of A minus. Now, the vast majority in a weak acid situation like this, in a buffer situation, of my dissociated species is going to be the stuff that I've went ahead and neutralized, if I've neutralized any of it. So this problem, it tells me that I'm putting in some amount of KOH, okay? And the vast majority of that A minus, the stuff that's associated, is going to be disassociated. It's going to be the A minus because I've reacted away the HA, the acid, using the KOH, which is the base. Okay? And so I'm saying right here that whatever amount moles of A minus I have, that's approximately the amount of moles of KH that I put in. Because that's going to be the vast majority of my conjugate base that's made is going to be due to that reaction of an acid and base. All right, so again here, right here, this is just the molarity. The definition of molarity is moles over liters. And so I was given 0.670 molarity KOH. That means I have 0.67 moles of KOH for every 1 liter. That's the definition of a molarity. And I went ahead and said, well, I want volume at the end of this, so I put the 1 liter on top and the 0.67 moles on the bottom. Well, I already figured out that my moles of KOH that I've used in this, well, it has to be something very, very close to this number here. So I go ahead and plug that in as my moles of KOH. 0.01296 moles of KOH, and I plug that in. I don't want liters at the end of this, I want milliliters, and so I divide by liters to cancel it out, and I multiply it by 1,000 milliliters, which is how many milliliters there is in a liter. And that gives me 19 milliliters. And that is actually the answer to the problem here. Again, make sure you do it for your own numbers though, okay? Okay, please let me know if this works or if you have any issues or any further questions or want to learn how to do these in your head because you're going to take the MCAT, whatever.